I mentioned already climate feedbacks and climate sensitivity. We will look at it again in just a tiny bit more detail. It's okay if I repeat few points because this is kind of the basic chapter which lays the groundwork, including terrestrial biosphere. So make sure you understand the concepts because we will go into various feedbacks and the other issues in the chapters that follow. To repeat our results from before, we have surplus energy in the lower latitudes and there is a deficit of energy in the higher latitudes. So there is a constant transport of energy by the atmosphere and the ocean from the low latitudes to the high latitudes. Nature doesn't like energy gradients. It always wants to smooth them out. So the most important thing to remember, in case it didn't already register, is that Earth is a sphere which creates these latitudinal energy flux variability because of the curvature and per unit area solar radiance received, and then you add albedo changes because of high latitude snow and ice and so on, and create these energy gradients and equator to pole temperature gradients, and then you add the tilt. It's going to amplify the seasonal contrasts from equator to poles and hemisphere to hemisphere. Okay, if we again quickly revisit our mean temperatures, this is air temperature close to the surface, which obviously looks pretty much like the ocean, but you can see that it's much more uniform across. So this is something called mean mixing ratio or humidity. So this is a relation between warm temperatures and high humidity. And so dry air in the polar latitudes with cold temperatures has very, very low humidity. Okay, these numbers here, basically it's a ratio of water vapor to the total air. So it's a dimensionless quantity mixing ratio. And this whole thing moves back and forth with seasons, with just like the IPCC. There are lots of beautiful details here that dynamically the tropics always tend to become uniform. So if you perturb something like with convection or with El Nino or a wave or whatever, dynamics tend to kind of even out the temperature gradient. So the tropospheric temperature gradient is very weak. So it has lots of dynamical significance that we will not get into. Talking about dynamics, there obviously leads to what we call climate feedbacks, but we will expand it to Earth system feedbacks because, as we talked about, there are also human feedbacks involved which we cannot ignore anymore. So the positive feedbacks here, for example, if temperature warms and evaporation increases, you will add more water vapor in the air because warmer air holds exponentially more water vapor. We will see that in a minute. Water vapor is a strong greenhouse gas, so it's going to trap more outgoing long wave radiation and further warm the temperature. Okay, at least in the warm latitudes, but everywhere. Even the polar latitudes, which are cold and dry, if they begin to warm, they begin to hold more moisture. Okay, there are potential negative feedbacks. For example, if this evaporation and warm air causes more clouds, especially the type of clouds that can reflect sunlight, then they can have a cooling effect or a negative feedback, right? Positive feedback is something that amplifies the initial perturbation and can have a runaway effect. Like, let's say on Venus, it has surface temperatures of 460 degrees centigrade, which cannot be easily explained by the distance from the sun compared to Earth, but it's because of the internal positive feedbacks. Okay, and more water vapor in the cloud can cause more clouds, but clouds can also trap outgoing long wave radiation and create positive feedback. For example, in general, cloudiness during the day can cool because it blocks sunlight, but at night it can block outgoing long wave and make it warmer. Okay, so there are all these positive and negative feedbacks in the system, and if we just look at quickly what is called the hydrologic cycle, because movement of water in the system is a very critical aspect of moving energy from the ocean into the atmosphere, moving it across to higher latitudes from the low latitudes as clouds and so on. So these are numbers that are in 10 to the 15 kilogram per year, so that's petagrams. Evaporation 413, which condenses. Atmosphere is typically not a big reservoir of humidity. You remember the gradient there. Tropics are humid, but not the high latitudes. A lot of it falls back as precipitation into the ocean, which has so much water there. And land also loses by evaporation and provides some rainfall to the ocean by advection, which is the carrying of the water vapor or clouds by winds. And ocean evaporated water and clouds get advected onto land and create precipitation, snow and ice. And there is also obviously sublimation, where you go directly from solid phase to vapor phase. And all that water that falls, or the snow that falls and freezes or melts, is very vital for the life cycle in terms of feeding vegetation, recharging groundwater, surface water, rivers that bring in nutrients into coastal waters, and the surface runoff that comes in as groundwater into the coastal waters as well, infiltration that happens, soil moisture that's maintained. So each of these then has to be looked at in terms of how they are responding to global warming. If you warm the air, do we necessarily get more rain, or are we going to lose more moisture? And if it rains more, where will it rain more? Everywhere, or only in some places? So in that context, we need to understand the climate sensitivity, which is kind of an integrated measure of how global warming is expected to respond to a doubling. So let me make sure that is corrected there, right? Reading it, climate sensitivity is the global warming expected for a doubling of atmospheric CO2 concentration after the atmosphere and ocean have come into equilibrium. So essentially, you somehow double the CO2 in the atmosphere, you ramp it up. If you do it at 1% a year or 2% a year, it takes a certain time, and then you hold it there till atmosphere and ocean come into equilibrium. So there is a transient response, which is what we are in now, and then there will be equilibrium response. That equilibrium response is called climate sensitivity. Okay, so you can simply write it as temperature change related to the flux change associated with the doubling of CO2 concentration. Okay, so if we go to our energy balance equation, where we looked at incoming shortwave with the albedo and approximate it as just ignoring the albedo effect and equate it to the outgoing long wave, then we get about 1 Kelvin warming for doubling of CO2 if no feedbacks are involved. It turns out that actually feedbacks are quite critical. How vegetation changes, desertification, distribution of clouds, which is a big unknown, ocean heat uptake, ocean CO2 uptake, and so on. I just want to show this because models and observations have difficulties estimating climate sensitivity because it's not constant over time. So it is generally looked at as very likely, likely, and most likely. So the ranges are different, and you can see that the temperature change in terms of climate sensitivity for the instrumental period, which is, let's say, from about 1850 to the present, is in this range here, with some extremes possible. Current climate state is supposed to be somewhere here. Climate models are depicting it over here, and if you estimate it for the last millennium based on the best data you get a much larger range. Volcanic eruptions can perturb the climate, and the climate has sensitivity to that. What data imply, what models imply for the last glacial maximum around 21,000 years ago. So it's encouraging, but you can see that the models have a larger range of likely and most likely climate sensitivities. Okay, lots of processes in the models. The amazing thing is that they give the models top of the atmosphere radiation, and they can do everything. They can do ITCZ, ocean circulation, winds, trade winds, westerlies, Hadley cell, Ferrel cell, polar cell, monsoons, El Niños, but they do them not so perfectly compared to nature. So we have to be aware of those. Millions of years ago, and combining different lines of evidence. This matters because, as we said, for projecting into the future, we need to be keenly able to nail down the climate sensitivity. As we increase greenhouse gases, what is the climate sensitivity that the system has is going to determine what changes will happen, how much warming we will get, but also what abrupt changes are possible, and so on.